Hello, my name is Elin, and in this presentation I will talk about how making better test models in the lab can lead to better medicine in the future. And more specifically, I will explain how microfluidics can be used to make blood vessels in the lab. Okay, so to make better medicine, we need to understand how they work. Medicines are chemical compounds made to treat or prevent disease, pain, and symptoms. Most of you have probably swallowed a pill once or twice. And these medicines enter our body and eventually get out into our bloodstream, where they get circulated and distributed across our body. We can also take them with injections, directly into the muscle tissues or the blood vessels. And the medicine can work and circulate faster. If we look at our body, we have many different tissues and organs, such as the heart, lungs, stomach, and kidneys. So how can the medicine reach the right place or the right organs? Well, if we picture our body as many doors, each door being an organ, and let's picture medicines as pizza. We get a pizza order from the kidneys and we have a key, so we can deliver the pizza. But my key works not only to the door that leads to the kidneys, but also to all the other doors. I am not sure which door leads to the kidneys, so I would open all the doors and give out some pizza until I reach the right door. But now I gave away most of the pizza slices. None of the organs are happy. The heart might not have been hungry, and perhaps the lungs and stomach wanted something else. And the kidneys are not happy since they only got one slice. Wouldn't it be better with a key that worked only to the kidneys so I could give them the entire pizza? And the other organs don't have to get something they didn't order. One way to target this is by using nanomedicine. Nanomedicines are very, very small compounds in the nanometer scale. They can be used as specific keys that find the right door. So you can carry and deliver the medicine or the pizza to the right place without disturbing any other tissues or organs that didn't want or need the medicine. The COVID-19 vaccine is a good example of a nanomedicine. The vaccine is transported inside a small nanoparticle shell that triggers specific cells, thereby delivering the vaccine only to the cells that needed it. But if nanomedicines are so great, then why don't we have more of them? So, this is me and my sister back in 2008. As you can see, a lot has happened. A lot of time has passed, almost 16 years. Now, if someone would have told me, would you like to spend roughly 10 billion Swedish crowns making something that won't be done until 2024 and most likely won't work, I would probably say, no. I don't want to spend so much money and time on something that won't work. Well, that is the reality of drug development, and we can't blame people for not wanting to do it. So why does it take so long, cost so much, and often fail to develop new medicines? Well, we need to go through the general process of making new medicines. First, we would need to find the chemicals. Then, we would test them out on animals and different models in the lab. If we get good results, we will go on to the human trials. Now, this is very expensive and takes around 8 to 9 years. If we get good results in the human trials as well, we will need to get our medicine approved before we can sell it. Not only is drug development a very expensive and time-consuming process, most of the time the drugs fail in the human trials, especially completely new drugs such as nanomedicines. So one way to improve the process is to get better results in the expensive and time-consuming human trials, so we don't need to do them again. How can we guarantee to get better results in these trials? Well, we can try to increase the clinical translation. But what is clinical translation, and how do we improve it? We can start with an example. In school, we might learn a new language, perhaps German. And then we might want to test our German. If we go to Germany, they will understand us. But then we want to try it in Spain. German in Spain is not going to work. So something that seems to work well in one place might not work in other places. So what does this mean in drug development? Before we can try our drugs out on humans, we need to perform a lot of tests on both the lab and in animals, mainly to look at the toxicity. Is our compound toxic? And also the dosage. How much can we take? If we have good results in the lab and in the animals, we can go on to the human trials. A good clinical translation would be that the results that we get in the lab and in the animals are the same as the results that we get in the human trials. The results are equal. Poor clinical translation is when we have good results in the animal and lab testing, but not in the human trials, and the results are not equal. We don't speak the same language and do not understand each other. And right now, this happens approximately 90% of the time. So, how do we change this? Well, we can try to make better models in the lab that look and act more like the human body. In other words, we can try to learn the same language that they speak in the country we want to visit. But how do we move from models that don't translate well to the human body to models that do? Well, we can try to copy the human body in the lab. And how do we do that? One example is to make a human blood vessel. But instead of inside the body of an actual person, we would grow a model of a blood vessel inside very small channels, so-called microfluidic channels, in the lab. The blood vessels can be seen as small channels with special cells surrounding them to keep the blood inside. So how do we make these small channels in the lab? The cells inside the blood vessel get their shape from the blood flow. So when the blood is being pumped by the heart, the cells change their shape. How can we give the cells in our model the right shape? Well, instead of having a human heart pump the blood, we could use a pump. Now, the blood vessel inside the microchannel in the lab looks more like the blood vessels in the body. Drug development is expensive. It's time-consuming and has a low chance of success. So we need to make models copying human body environments, such as fluid flow through blood vessels, so they can work as they do in the human body. With more human-like models in the lab, we will get better clinical translation. In other words, the language that we learn in the lab is the same that the human body speaks. So we waste less money and less time, and more drug development can be done. Which means we can get better medicines and finally have the right key to the right door, so we can deliver the pizza to the right place. Thank you for listening.